Hello and welcome back. We are talking about functional models from section 1.4. This is our third and final learning objective to tackle: investigate market equilibrium and break-even analysis in economics. So we've talked about some general modeling procedures, and now we're going to talk about some problems very specific to economics applications. So market equilibrium, probably should define that first before we get too far. So if we're given supply and demand functions, you might recall these either from your economics course or perhaps from section 1.1 of the textbook. Supply function models how much producers are willing to make at a given price. Demand function models how much consumers are willing to purchase at a given price. And market equilibrium is supposed to be the place where these two graphs intersect. So that is where supply is equal to demand. Then the two other scenarios when we're not equal are if supply is greater than demand, then we say that there's a surplus, and then if we run into the scenario where supply is less than demand, then we say there's a shortage. You could also call surplus excess demand or shortage excess supply. Consumers of a coffee shop are willing to buy 150 frappuccinos every hour at a price of $3 each. However, the coffee shop is only willing to supply 100 of them at that price. Perhaps it has to do with staffing or other considerations. But if they were able to charge $4, then consumers are only going to buy 100, but the coffee shop would be happier making 175 of those. Okay, so our task is to find linear equations for supply, demand, and then we're supposed to identify the price at which market equilibrium is found. So there's really three distinct tasks here. We need a supply equation, a demand equation, and a price. And you might notice they do us a solid here by saying that these equations are linear. Otherwise, we'd kind of be just lost in the woods there of all the different types of equations to work with. So it is handy they say linear. Okay, so supply was the first thing they said, so let's tackle that first. Equation for supply can be found by letting number of frappuccinos be y and the input price be p. You're really kind of, it's up to you whether you choose output to be price or number of units of, I guess in this case, coffee sold. I think there's an argument that it makes sense to have price be the input and have number sold be the output, as in this case. But it's certainly possible to do that the other way, and there are definitely instances we run into where price is the output and units sold is the input. Okay, so what we're given in the original question, though, amounts to these 2 points. We were told that at a selling price of 3, the coffee shop would be willing to supply 100 of them. If their price went up to 4, they'd be even more excited about that, and they would say, for instance, increase their staffing such that they would be supplying 175 of these frappuccinos. So we're told it's a linear function, so we get a line out of this. And the most interesting characteristic, the first thing we can figure out, is the slope of that line. So we do y2 minus y1 is 75 on top. x2 minus x1, 4 minus 3 is 1. So 75 over 1, great, 75. So we have the slope of our supply function. And then since we have at least 1 point, just going back a moment, we've got 3, 100 and 4, 175. We've got a slope. So really, we could choose either of these to work with. I think 3, 100 is the tidier, just because it's got those zeros on it, makes it easier to work with. But we'll use the slope and one of these 2 points. It doesn't matter. We'll get the same equation no matter which of those. But I think I picked 3, 100 using that slope point slope formula. So there's our input 3, our x value, our y value, the slope, and then the p value is taking the role of x in this case. So great, we have a little distribution, 75p. 75 times 3 is negative 125, but, negative 225, but then we have to add 100 over. So our final constant for this piece is negative 225 plus 100, so negative 125. And then the equation that defines supply looks like this in function notation, all fancied up with its tucks on. So instead of just y, now it's s of p. The name of the function is s, and the input is p. Now we know the same set of information about demand. We have to extract this from the words like we did before, but it's still possible to work this out just by snagging English and turning it into math, in this case, turning it into points. When the Frappuccinos cost $3, consumers were willing to get 150 of them. When it went up to 4, some of these people got discouraged, so when charging $4, the demand went down to the quantity demanded. Your econ professor would get mad at me for saying that, for saying just demand. The quantity demanded would go down to 100, which you'd imagine. If you charge more, generally you get fewer customers. Slope of the line then, using y2 and y1, would be negative 50 on top, and then the same x values, 4 minus 3, so now we're down to 1 on bottom. Negative 50 over 1 is still 1. And then putting the equation together with the point slope formula, we've got output, input, and I picked, again, it doesn't matter which of these 2 points we work with, but I picked the one with the tidier numbers in some sense, so using 100 as opposed to 150. But either point will do. And then with distribution, negative 50p, this time plus 200, and then we add another 100 onto it, giving us our constant term of 300. So then written in function notation, it looks like d of p, d for demand, and p, the input of this function, negative 50p plus 300. Okay, now what we're supposed to find is market equilibrium. We've accomplished supply function, demand function, and then market equilibrium is where these two things are equal to one another, where demand and supply are the same. So we'll just snag our demand function from the previous slide, the supply function from a couple of slides ago, and set them equal. And I think I subtracted negative 50 minus 75p to get negative 125p on the left side, and then subtracted the 300 over to get negative 425. And then finally dividing everybody by negative 125 gives us a nice p equals 3.4. And as usual, when these problems are stated with words to begin with, it's always polite to return to words at the end. So what we could say is that market equilibrium is found when we charge $3.40 for each Frappuccino. That's what P was, a unit price per Frappuccino. And we've accomplished all our goals. One additional economics application that we're going to take a look at, or perhaps we could think of this as business. So if you look at profit and you find zero profit, it doesn't sound like a great thing, but break even, I suppose, is at least better than a loss. So if profit is equal to 0, the piece of terminology we're exploring is that we call this a break-even value. So if we have an x that causes this to happen, that's a break-even value. And because of how profit is defined, it's the difference of revenue and cost, R minus C, then it's also the same thing to say that break-even happens when revenue equals cost. That's an equivalent definition for this break-even point. Sometimes it's more convenient if you're given these two functions, you don't have to build profit and then set it equal to 0 to solve. You can just set these two equal. And it makes sense too. The gross amount of money you take in being equal to how much you expend to make these products, well, then you're not going to be making any profit on top. So let's try one of these out. We'll go back to good old Milton and his Audi Sports, the spark plugs for his Audi cars. So he buys them at $3 each, and then he spends $11 in daily labor to sell these things, and then we've got a demand function, 15 minus x, and this is a unit price per plug. And our task here is to find the break-even point for the sale of these things. Okay. So just by definition, break-even point happens when revenue is equal to cost. So if we can build a cost function and a revenue function, then we should be in good shape. So recall that Milton's Auto Parts pays $3 each to buy these from the manufacturer. That's actually part of his cost formula, because it's surprisingly sociological, but you have to put yourself in the perspective of Milton's Auto Parts in this scenario. So a cost to this company includes purchasing them from the manufacturers. So he's going to pay, or this company is going to pay $3 per spark plug. That's the unit cost for each of these items. And then since we're thinking about a daily cost, then he pays fixed $11 in daily wages that is associated with selling this particular product. So his cost function, variable cost, is going to be made up of 3x. And then the fixed cost is the daily labor associated with this. So there's his completed cost function, where X is the number of plugs that he buys. Now, this demand function, and this is one of the kind of flips that we have to do, this demand function is actually a price. It's describing the unit price for each of these plugs, and then it's depending on how many you could think, wants to sell, for instance. So X is the number of plugs that's being sold here. So the more expensive, well, the more he wants to sell, the lower his price has to be. Okay, but demand itself isn't revenue. Revenue is built out of the number of units you sell, X, times how much you charge per item, D in this case. So 15 minus X is the demand function, so we can just snag this from up above and use that in our revenue function here. With a little bit of distribution, we've got 15x minus x squared. Okay, so we've got a revenue function, we've got a cost function, and remember that what we were after was really break even. So we need C of x to be equal to R of x. So our setup and solve takes our C of x from on the left side there, 3x plus 11. It takes R of x, 15x minus x squared. And we probably want to put some of this stuff together. For instance, you'll note that we have things in common, 15x on this side and 3x on the other. Those, if we subtract 15x over, we can get ourselves just x terms on the left. And then we've got x squared, but keep in mind that the challenge we're facing here is we have x squared terms and regular old x terms. Those are not like terms. They aren't going to combine with one another. So one key strategy that we can make use of is factoring, A, if it'll work out, or B, we've always got the quadratic formula to resort to. Sometimes it's kind of like using a bazooka on a mosquito, but we've always got quadratic formula to solve equations that have x squareds and x's in them. So we can add x squared to both sides and get ourselves a function that, an equation that has all of our variables in one place, and that's advantageous for either factoring or the quadratic formula. Turns out this factors nicely. So for instance, if we look at 11, 1 and 11 multiply together to give you that. If we want the middle term to be negative, though, we should make each of these terms negative. And then conveniently, negative 1x minus 11x gives us this middle term. Negative 1 times negative 11 also gives us positive 11. So this actually is a valid factorization of this expression here on the left. Which is delightful, because if you have two things getting multiplied together, set equal to 0, that means that you can break off one or the other of these equations and set them in turn equal to 0. So x minus 1 equals 0 implies x is equal to 1. X minus 11 equals 0 implies that x is equal to 11. And then our conclusion from this is Milton's Auto Parts breaks even when they sell either 1 or 11 plugs. Perhaps in the middle of these two things is something nice where they actually make a positive profit. That's the last video for section 1.4. I hope I'll see you for section 1.5 soon.